Good morning, chemistry team. Chemistry coach coming at you with video number 4 in our chemical reactions series. Today we're looking at limiting reactants. Nothing really new, right? There's almost this entire concept. The only thing that's new is the stoichiometric factor, that mole to mole ratio, to go from one species in a balanced chemical equation to another, whether it's reactant to product, product backwards to reactant, reactant to reactant, product to product, doesn't matter. Just connect any two by those numbers. That's it. And it gives us an infinite possibility of different types of problems that I could give you on your tests. Yay! I could take any reaction and have a whole bunch of different types of questions. But what we run into, we really simplify things a lot, but in the real world, like in a lab or something, if we're taking reactant A and reactant B and mixing them together and trying to figure out how much we produce of those products, well, it depends how much we're starting with of each one. We tend to make an assumption that we'll say, hey, so you got 10 grams of this species, and we don't even mention the other one. There's an assumption involved with that there's exactly the right amount of the other reactant to completely react with the one we're interested in, call it stoichiometric amounts, or there's excess of that. It's usually not stated in the problem, it's assumed. But in the real world, a lot of times you'll have, X amount of reactant A and Y amount of reactant B, and then you got to figure out how much product you form. It really is based on which one runs out first, right? So when we have at least two reactants, usually two, but sometimes 3 or 4 or more, I hope this makes common sense, the one that runs out first will stop the reaction. So once a reactant runs out, you cannot run the reaction anymore. So that sets the maximum amount of product that can be made or produced in that particular reaction, just like when you're cooking, right? If I need 13, I'm not a cook, so I should say I need 13 cups of flour and 5 cups of sugar, and I look in my cupboards and I got 25 cups of flour. I got more flour than I could ever need, but I only got 1 cup of sugar. I'm like, crud monkeys, I don't have enough sugar. So that's going to limit the amount of whatever the heck I'm cooking, pastry, cake, whatever. So I would have to adjust my ratios to match the one that limits it. I can only make so much because I'm limited by this particular species. For example, let's say we got a reaction like this. This is probably something you haven't seen. I think that's potassium superoxide, probably a polyatomic ion, O2 with a -1 charge, probably haven't seen, and some carbon dioxide. I've seen people use this to extract carbon dioxide out of the air. If you've ever seen a movie where people are in some capsule or something like that and they're exhaling, producing carbon dioxide, and they don't have any way to purify that out of there, get that out of there and scrub it out, they can die, right? And it builds up to toxic levels. They can asphyxiate there. So they can use this as a scrubber per se, pull the carbon dioxide out, pulling that carbon into potassium carbonate and generating oxygen gas so you can keep on breathing. Oh, there's a really cool movie that had that. Space movie with a scene. See if you can figure out what movie that was. It was a really cool movie based on reality. You'll always recognize a limiting reactant problem because when we write the problem, say on a homework or a test or something, you'll have amounts of all the different, well, at least 2, but usually all the different reactants. That's your red flag. You go, ding, 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 this is going to be a limiting reactant problem. Commonly, we'll just say, hey, if I have, say, 143.4 centigrams of potassium superoxide, how much oxygen can form? And I don't say anything about the carbon dioxide. We're assuming there's a stoichiometric amount of carbon dioxide. When the KO2 runs out, this runs out exactly, theoretically, right? That's probably not going to happen in the real world. Or we have so much carbon dioxide that this runs out first and determines how much oxygen we form. Or if I just give you the carbon dioxide, we're assuming that there's just enough potassium superoxide or an excess amount of that. But when I give you both, you go, oh man, how do I know how much of a product, in this case, let's say how much oxygen can form? We're not going to, I've seen several different ways people teach limiting reactant problems. There's some tricky little algebraic ratio deals. I'm not going to do any tricks. I'm just going to go based on stuff we already know. We're just going to use stoichiometry. We're going to treat this like a twofer. 2 problems for 1. It's a 2 for 1 special, yay! So all I'm going to do is I'm just going to take reactant number 1, in this case potassium superoxide, take that starting amount, and then figure how much oxygen forms in that. Whatever units, could be moles, could be grams, it doesn't really matter. And then I'll do exactly the same thing in the second line and take the other reactant, in this case carbon dioxide. Take that starting amount and convert that also to oxygen, whatever amount that is. Moles, grams, doesn't matter. But they have to be the same. And we're going to compare these two. You can't compare this to this. You have to get them both into the same thing. Apples versus apples, oranges versus oranges, right? So we could convert both of these to, say, moles of oxygen, or both of these to grams of oxygen, whatever you need, and then compare them. Because look, the mole ratios are different, right? The masses are different. Potassium superoxide reacts 4 moles of that, produces 3 moles of oxygen, 4-to-3 ratio. But the carbon dioxide is a 2-to-3 ratio, right? So you're burning up way more potassium superoxide to produce the same amount of oxygen. So even though I have more, I have different units here, I'm going to throw this in there. So whether you have more of one reactant than another, you can't compare these numbers. That you have to get them into the product first, apples to apples. And then the one that's lower, all right, so I'll convert this to, say, moles of oxygen, and then this one to moles of oxygen, and compare those two. The one that's lower would be the one that limits the amount of product you can form. Let's set that up on the next board here and kind of go through that game plan of how to attack it. So it's really just a stoichiometry problem, but twice as long. You got to do both reactants, pick the one that gives you the lower amount of product, and you're done. So it's not difficult, it's just a little bit longer. So let's transfer this problem onto the next board, go through our approach on how to do it, and then figure out what our answer is. Yay! So when the key to these is recognizing a limiting reactant problem. You're on an exam or a quiz, and you're like, oh, okay, so here's the balanced chemical equation. Hopefully your professor provides you that. Otherwise, you got to balance it or predict the products. And then you read through the problem and go, oh, there's a given amount of this reactant and a given amount of that reactant. And you're like, oh, man, okay, this is a limiting reactant problem. But you've done the homework, and you've practiced, and you recognize and go, okay, I know what to do now. So here's what you do. Depending on your professor. I've seen different professors teach different ways, and that's okay. Do the way your current professor is teaching you. Oh, they're your coach. So what we're going to do is we're going to take each reactant, like I mentioned earlier, and do them separately, use stoichiometry, and convert each provided amount of the specific reactant, convert it to the product of interest, whatever is being asked for. You could really do any product, but you might as well do the one we're solving for, and the other one would be irrelevant. And again, you don't have to do it to moles. You could do it to whatever. Say they're asking for grams or milligrams or milliliters. You could convert it to that if you want to, but at least get it to the moles of the product. So both reactants have been converted to moles of the exact same product. That's why I say you're comparing apples to apples. You have to do that before you can compare them. Now, we're going to label each reactant a certain way. The limiting reactant, I've seen people say limiting reagent or limiting reactant, whoop-de-doo, is the one that produces the lower or lesser amount of moles of the product. And that's the one that's going to run out first. There will be none left after the reaction's over. Once that limiting reactant runs out, boom, the reaction stops, and the amount of product you form is now set. That would be the maximum amount you can form. The other reactant that doesn't run out, we call that the excess reactant, or we say that's the one that's in excess. So that reactant has the greater amount, because you're going to get two answers. Reactant A gives you this much of product. Reactant B gives you this much of product. One's going to be higher, one's going to be lower, right? So the one that's lower tells you which was the limiting reactant. The one that's higher tells you which reactant was in excess. So once that reaction stops and the reactant that runs out, the limiting reactant, is gone, boom, reaction's done. There's going to be some left over of the other reactant where you have too much of it. We can actually determine that amount using stoichiometry. I usually don't do that on my exams. I'm usually interested in the product. But you'll see in the homework a situation where we're not going to worry about the product. We're going to say, hey, if you have this much of reactant A and this much of reactant B, how much of the one that's in excess is left over after the reaction stops? So you're just comparing the stoichiometry between the two reactants. It's pretty easy to do. And it can be calculated. But now that I'm just looking at the terminology, I want you to identify very specifically which reactant is the limiting reactant and which reactant is in excess. So let's go back to that original problem we put up and let's solve it See if you can do it ahead of me. Nothing new. There's no bag of tricks here. Just take the first reactant, the potassium superoxide, and the amount I gave you. Boom! How many moles of oxygen gas form? Then take the second reactant, the carbon dioxide gas. Take the amount that was provided. Boom! How many moles of O2 gas can form? Which one's lower? Right? That tells you which reactant was limiting. Take that lower moles of oxygen, convert it into whatever units are asked for, which I haven't done that because I haven't given you the problem yet. So let me write that up on the board, but you can at least get to moles of O2 before I do this. How about it, my friend? Got a problem back up on the board, so this is kind of how it would be phrased in a problem on a test or something. So how many milligrams? So I'm just being a booger head instead of saying grams. Oh, we got to do the metric conversion. I always like slipping those in just to make sure you're on the ball. How many milligrams of oxygen gas? So when I'm reading this problem on a test, I go, okay, solving for milligrams of that. That's my goal, just like you're planning a vacation. The first question you ask yourself when you're going on vacation is, where are we going? Yay. And then the second thing you go, where are we starting from? And then you can do the maps and stuff. All right, how many milligrams of oxygen can form when? Okay, so we've got a certain mass of potassium superoxide, so I'm going to pop that in there. So we got 143.4 centigrams of that reactant are reacted with 0.92 grams of the other one. So we have 0.92 grams of that. And we want milligrams formed. So we know this is a limiting reactant problem because I gave you both. If I just gave you one, we're assuming the other one is in the exact stoichiometric amount or in excess. So we go, crud monkeys. This is the big problem on the exam, probably worth 15, 20 points, that kind of thing. Once you know how to do it, it's easy points. You just start go into Chem Zen mode. I can do this. And I know I have to do two separately. So here we go. What we're going to do is we're going to take the KO2. So we're going to take the 143.4 centigrams of potassium superoxide and figure out how many moles of oxygen gas that can form. Think of that as a part A. It's not really part A, part B, but you have to do that. And then we're also going to do it for the CO2. Then we're going to take the 0.92 grams of carbon dioxide and figure out exactly the same thing. How many moles of the product of interest? You can't compare moles of KO2 to moles of CO2. No. That's comparing pineapple to anchovies. You can't do that. Got to get them both into the exact same species in the exact same units. Now, you could do that straight to milligrams. If you want to do both of those to milligrams of O2, you're welcome to do that. And then the lower one is your answer. Or you can just go straight to moles, and then once you get the lower one, take that, and then continue on, convert moles to grams, then grams to milligrams. So go ahead and do that for me. Hopefully you already did it. Obviously, I'm going to need another board for that. And we'll just do them side by side, see which one gives us the lower answer. The lower one is the correct one because that's the one that comes from the limiting reactant. So while you're doing this problem and finishing it up, let me set up my board again. I need like a huge board, but it wouldn't fit on the screen, would it? Ready to work through this together, my friends? So we've got two problems to do. Here we go. Let's start. I don't care which one you start with. That's completely irrelevant to me. So let's just start. I'm very systematic. Let's just take first reactant. Take the potassium superoxide, 143.4 centigrams. I think that's what was provided. And just like we did before, whatever you're provided in stoichiometrical problems, convert that to moles. We got to get to moles of KO2 in order to get to the 4:3 ratio there, right? So we're going to have to go centigrams to grams using the metric conversion, using the molar mass to go from grams to moles, and then we can use the stoichiometric factor to go from moles of KO2 to moles of O2. Hopefully you did that already. So let's do it. Let's convert centigrams to grams. So we know there's 100 centigrams per gram with the assumption, obviously, that's KO2. Now we need to calculate the molar mass of potassium superoxide. We get our trusty periodic table. So we're going to have one potassium, and mine says 39.0983. See that? 39.0983. Good to 4 decimal places. And then we're going to add 2 oxygens to that, 15.9994. Good to 4 decimal places. So they're both to 4 decimal places, so our answer is going to be good to 4 decimal places. pop those out on your calculator, see if you match what I got. 71.0971. So 71.0971 grams of potassium superoxide per mole. Right? Early stuff we did. You're doing molar masses all the time. That's the ugliest looking gram I've ever seen. And then if you want to cancel out your units, you're welcome to. So centigrams cancels out. Grams cancels out. Now we're in moles. Whatever you do, get to moles. And now I can take the 4 moles of KO2 forming 3 moles of oxygen. So 4 moles of our reactant gives us 3 moles of our product. Cancel that out. Basic stoichiometry, you do this all, as a chemist, you should be able to do this with your eyes closed and your brain off all day long, all the time. You love dimensional analysis stuff. We've got 4 significant digits here. Metric conversions are exact. Molar masses rarely limit you, so we've got 1, 2, 3, 4, 5, 6 there. Remember, stoichiometric factors are exact, so we're limited to 4 significant digits in this. So this gives us, if you punch this out, 0.01512. Put the vertical dash line after the 4th significant digit. 71 moles of oxygen. Right? So if that was the limiting reactant, that's how much it would produce. But we don't know if it's the limiting reactant. We got to test the carbon dioxide now. Let's do the exact same thing for carbon dioxide. We are given grams, so let's just use the molar mass, go directly to moles. 1 carbon plus 2 oxygens. You can bang that out pretty quick. And then once we got moles of CO2, 2 moles of CO2 produces 3 moles of O2. So it's exactly the same as this one, just without the irritating metric conversion, right? So here we go. So we got to take the carbon, and depending what periodic table you use, this one has 12.011. I've seen 12.0108. Some people use 12.0. Some people use 12.01. Use what's on this. Yes. So let's take one of those, limited to 3 decimals, plus 2 oxygens, 15.9994 times 2, 9994. That's to 4 decimals. So our answer would be good to 3 decimals places based on what's given on that periodic table. So I get 44.0098 grams of CO2 per mole. And I put the vertical dash line between the 9 and the 8 because we're limited to 3 decimal places. Now we got moles of CO2. You can cross out the units if you want. Grams of CO2 goes bye-bye. And now I can go from the 2 moles of CO2 to the 3 moles of oxygen. 2 moles carbon dioxide will produce 3 moles of O2. And you see why you can't compare KO2 to CO2 because the mole ratios are different. This is a 3 to 4 mole ratio producing oxygen. That's a 3 to 2 mole ratio. Those are different. And we can cancel out this. It's just a two problems of stoichiometry in one umbrella, right? So when we punch this out, let's see, we got 2 significant digits in the mass, 5 in the molar mass. This is exact, so we're going to 2 significant digits here. I get 0.031. There's my 2 sig figs. So put that vertical dash line. 35 moles of oxygen. So the grunt works out of the way. Now I can compare these two. 0.0151271, 0.03135. Can you see that this is lower than this one? So I'm going to write that in there. So let's do that in blue. So this is lower, and this is higher. Please don't screw that one up on the test. Right? That's usually where I get all the hard stuff. Then I'm like, oh, I got it, and then I fall on my face at the finish line. I'm like, I hate it when that happens. So this one's lower. That means KO2. A lot of times you'll see LR is the limiting reactant, and the CO2 is in excess. I keep wanting to do the band, INXS, right, in excess. Makes you sweat. So I've identified which one's my limiting reactant, the potassium superoxide will produce less amount of oxygen, so that will run out first. And I'll have excess carbon dioxide when it's done. And I could solve for how much excess carbon dioxide, how many grams or milligrams or whatever, if I wanted to, but wasn't asked for in this problem. So now that we've identified our limiting reactant, let's take that. Let's take that lower value, come down, convert it to whatever units were asked for. What were we asking for? Was it, I don't think it was grams. I think it was being a meanie, milligrams, I think, right? So let's convert that from moles of oxygen to grams of oxygen to milligrams of oxygen. So let's get the milligrams of O2. So that will be 0.01512. 71. So I'm just taking that number. Now you can, if you have room on your paper, you can just continue it over there too, off the screen. Right? You can just take that and just do the conversion if you don't want to rewrite it. I don't care as long as I can see what you're doing. So let's convert moles of oxygen to grams. So let's take that molar mass, 15.9994 times 2. That'll be oxygen plus oxygen, so that'll be good to 4 decimal places. So let's take the 31.9988 grams of oxygen. And if I'd only asked for grams, we'd be done. But no, I was a booger. I asked for milligrams. So let's convert that. So there are 1,000 milligrams. I'm starting to butt up against my other stuff here. I've got 4 significant digits here. Correct, in the moles, because that came from this one. Now, I know if you did this correctly, just based on the number of significant digits in your answer. If you have 2 significant digits in your answer, I know you did it from CO2 and you got the wrong limiting reactant. If you have 4 significant digits, I know you got the right one. So I can just look immediately and know if you're tracking your uncertainty correctly, of course. So 4 significant digits here, we've got 6 there. This is exact, so we're going to be limited to 4. And when you punch this out, I get 484.049. So 484.0, there's my 4 significant digits. So let's put a little vertical dash line. 49 milligrams of oxygen. That's less than 5, right? So I don't round up. It's closer to 484.0 than it is to 484.1. So that'll stay at 484.0. So 484.0 milligrams of oxygen. So not difficult, just a longer problem than normal stoichiometry. This is more what you run into in the real world all the time because you have specific amounts of each reactant. That's how you do it every single time. Right? And again, you might read, if you have another professor, you might see some fancy trick to predict which one's the limiting reactant ahead of time and blah, blah, blah. Just more crud than you need to memorize, right? So just here, you don't have to learn anything new. Just go, hey, do this one, pick the lower one, done. There you go. Limiting reactants. Boom! One extension of stoichiometry.